Hi class, today we're going to be focusing on Chapter 11, switch features. There's two types of switches that we're going to talk about right now, unmanaged switches and managed switches. For unmanaged switches, techs have little to no control over how they work. They use something called a data plane or forwarding plane, and essentially it is just optimized components that make the switch work. So optimized hardware components that make the switch work. Conversely, managed switches have operating systems and they enable device configuration. They have a control plane with an extra layer of software and hardware configuration. Let's talk about connecting to a managed switch. There's three main methods. One, you will just plug in directly to a serial or console interface. You can use a virtual terminal program, something like PuTTY. You can attach the switch to a network and then use something like SSH to connect to a command line interface. You can also connect the switch to a network and use something like the switch's built-in web interface. Connect using a console port. So again, here we have a little image of what that would be like. You have your little console port that you plug into, or your console cable that you plug into the back of the switch. And the other end will go to your laptop or whatever device you're using to configure your switch. Again, once you plug in the cable from the switch to your device, you'll use something like a terminal program, something like PuTTY, to enter the command line interface and begin configuring your switch. This is often done for the initial configuration of a new managed switch. Connecting using a virtual terminal or built-in web interface. This will require an IP address. Here's what the steps would look like. Connect the switch over the network and then manage the switch using some kind of software. Again, our go-to example here that we're using is just PuTTY or a web browser. One thing that may seem a little counterintuitive is that a managed switch needs an IP address. And we often think about switches as layer 2 devices exclusively, or at least that's the way we mostly have talked about them up to this point. Again, I've mentioned a few times that there are multi-layer switches or switches that have higher functionality, and we're going to talk about that a little bit more in this chapter. New out-of-the-box managed switches can have some of the same issues that a router will have. You have to go through the initial setup and configuration. They're not plug and play in the same way that an unmanaged switch is. Managed switches will often have a default IP address and a default username and password right out of the box. So often it is a very good practice or very important for security reasons to configure a new IP address and a new username and password. So you want to change those as quickly as possible. Let's talk about access management. We have in-band management. This is managing the switch from the same network that moves data. So this can be connected locally or remotely, as long as it's on the same network. Out-of-band management is about exactly what it sounds like, managing the switch from outside the network, usually via a separate network set up just to manage and monitor switches. We've talked about this before, but I'm going to go ahead and briefly run through it again. I don't have it up here on the slide, but there's something called simplex. It's where we can send data over our lines in one direction and one direction only. Then we have half duplex, and that's where data can go in either direction, but it can only do it one at a time. So traffic can only flow in one direction at a time. Then we have to wait to receive or send data. So it can't go in both ways at once. Then we have full duplex, and that is where data can go both ways at the same time. So full duplex, data can send or devices can send and receive data at the same time. So again, full duplex, we can send and receive data at the same time. Flow control. So this is just a concept around managing traffic or managing the flow of traffic. We have something important, a concept called a pause frame. And essentially this is where our device or whatever it may be asks a switch to kind of pause transmission or communication for a little bit. Usually this can happen when a host is currently being overwhelmed by too much data or too much communication. And it helps it to kind of manage that stuff a little more efficiently so it's not being overwhelmed. If the host device catches up earlier than expected, it will send another pause frame to the switch, which may sound counterintuitive, but the pause frame will have a 0-second delay. So we'll just send a pause frame with a 0-second delay. It's essentially telling the switch, hey, please wait 0 seconds to start communicating again. So then the switch will start communicating immediately back with their device. This can cause some issues or latency problems with things that need to be sort of live streamed out like VoIP. So often there are other methods used to manage that kind of traffic, like QoS. We'll talk about that later. Jumbo frames. These can be used in special purposes for certain types of network. So we talked about how frames have very specific sizes that they need to be. If there's a frame that doesn't have enough data, how we talked about how we'll use something called padding to make it reach the size that it needs to be. However, in certain situations on our own networks, we can use something called a jumbo frame, where we're actually making them larger than the normal 1500 byte payload that we would normally be limited to by the IEEE 802.3 standards. It's an inexpensive way to boost performance. It improves the payload to overhead ratio. The way your book phrases this is that WANs may not respect jumbo frames. So again, if we're trying to communicate out over the internet with these jumbo frames, we may run into issues. So one may be fragmentation, where it breaks those frames back apart into smaller frames, or sometimes we may get dropped packets altogether. So again, in our own network, it's easy to configure our own devices to handle jumbo frames and kind of work together on that. But sometimes when we're communicating out over a wider network, we may end up having some trouble. Port security. And again, we're not talking about the logical ports that we've been talking about at other times in this semester. We're talking about physical ports on our switches. One thing we can do is lock a port to only work with specific MAC addresses. So again, ideally, every device has its own unique MAC address, and so we can set it up so that only certain devices can communicate on certain ports. Cisco allows sticky or persistent MAC addresses. These can be dynamically learned or manually configured. They're stored in the address table. Again, we can add these to the running configuration. This will mean that when we restart the switch, we won't have to dynamically relearn them all over again. Today's networks or LANs can be fairly complex. We have to deal with things like remote incoming connections, public web or email servers, strings of connected switches, a tremendous amount of traffic, security challenge. Ideally, we would like a way to segment different networks without adding a bunch of additional hardware. Let's talk about how we do that. One of the kind of key solutions that is very, very popular is something called a VLAN, virtual local area network. Essentially, what a VLAN does is it enables segmentation of a network using switches. So again, we're enabling segmentation of a network using switches. We're creating virtual LANs using switches. To create a VLAN, we take a single physical broadcast domain and we break it into multiple broadcast domains. We create two VLANs. So we could have something like a VLAN 1 or a VLAN 2. You could actually have hundreds or countless VLANs on a specific switch. But just for this example, we're just saying simply you would have at least two VLANs. We'd assign some ports to work as VLAN 1 on our switch, and we would assign other ports to work as VLAN 2. Traffic sent from a host plugged into a port for VLAN 1 becomes part of the broadcast domain for VLAN 1. Okay, and then we have a picture up here that will kind of highlight what's going on with that. So normally, these type of switches that are configured to support VLANs will always have at least one VLAN. By default, everything will go to VLAN 1. So when we plug in as many devices as we want into our switch, they will all be grouped into this one big VLAN. However, if we wanted to create multiple virtual local area networks, we could configure some ports on a switch to be their own separate network, and then some ports on the switch to be their own network. So in this case, we have some of these devices plugged into a switch and they're configured to be VLAN 1, and the other devices are considered to be VLAN 2. So these are each independent broadcast domains. So I'm going to say that last part again. Each of these will be independent, their own broadcast domains. Trunking. Okay, this one is kind of a tricky concept, but once it clicks, it's not so bad. The idea is just transferring VLAN traffic between switches. So again, we just talked about that example before where we have one switch and we created two broadcast domains with our one switch. So we had a VLAN 1 broadcast domain and then we had VLAN 2 all plugged into that one switch. Well, we can kind of extend that functionality if we used multiple switches. So we could have VLAN 1 be on our second switch here and on our first switch here. It's managed through a process called trunking on trunk ports. So we use trunk ports on the switch. We use this process called trunking to manage that traffic. So even though it may seem very counterintuitive, this VLAN 1 and this VLAN 1 over here are all part of one broadcast domain, even though they are on separate switches. And again, over here, this VLAN 2 and this VLAN 2, even though, again, they're on separate switches here, they are treated as if they are all part of the same broadcast domain. We use something called the IEEE 802.1q standard. So it's the trunking standard that every Ethernet switch uses today. Connect switches from different manufacturers. So again, it's a standard that applies across multiple switch manufacturers. Okay, so how do they make that work? They do something called port tagging, and essentially all it is they will add this 802.1q port tag to the data as it's being passed around. Specifically, it will be tacked on to the frame's Ethernet header. So we'll tag this we'll put this 802.1q tag on the frame's Ethernet header. And this will let the switches know which VLAN that's supposed to go to, what is the correct VLAN for that tag. An important note here, tags are on frames as they transit the trunk lines between switches. They are not on lines between normal switches and regular hosts. So it's only on the trunk lines. Access ports are just untagged ports. So again, I'm going to say that again. Access ports are untagged ports. These just deal with regular host devices. They're standard switch ports that are associated with untagged traffic. So again, access ports connect to hosts, just regular hosts on our system or on our network. Trunk ports connect to other trunk ports. Trunk ports connect to other trunk ports. These switches also have something called a native VLAN, and it's kind of a special VLAN out of that whole list of VLANs there. It's associated with untagged traffic. So again, this is going to be the only type of VLAN traffic that is associated with untagged traffic. So again, there's no tag needed for traffic or communication going over a native VLAN. The 802.1q tag will be added to the frame if it's part of any other VLAN. Native VLANs serve a few purposes. One is they provide compatibility with older switches. Some of the older switches don't support the 802.1q standard, or tagging. So what they can do, again, what this native VLAN does is makes it so that you can still work with older switches. This does, however, open you up to a potential attack. It's called the double tagging attack, and it will allow an intruder to gain access to unauthorized VLANs. Modern networks can defend against this in a couple ways. So by default, most VLANs will have the native VLAN set as VLAN 1. So that by default, that's usually the native VLAN is VLAN 1. What you can do is configure or change the settings to move the native VLAN to an unused VLAN. You can also configure the trunk port to tag native VLAN traffic. VLAN trunking protocol, VTP. Large networks with many VLANs require intense work to update. So we have something called the virtual trunking protocol. This is a proprietary Cisco protocol. It automates updates to multiple VLAN switches. 3 switch states, we have a server, client, or transparent. Updating VTP server switch configurations will update connected VTP clients and VTP servers in minutes. Transparent state does not update, but can still pass on updates. So again, if we wanted to ensure that something doesn't update for whatever reason, we can set it to that transparent mode, but it will still pass along updates to other switches. Inter-VLAN routing. This is the process of passing traffic between 2 VLANs. So again, normally when we want to communicate between 2 networks, we need a router or some kind of router-like functionality. And so since we just created multiple broadcast domains or sort of multiple networks with our VLANs, we need a router or some router-like functionality for communication to happen between those broadcast domains. We have 3 common different options that you might encounter. One is the kind of simplest, most straightforward option, which is each switch will just be plugged directly into a port on the router. You can run out of ports on your router very, very quickly like this, so it's not very scalable. This first option is just not very scalable. Another choice is something called a router on a stick configuration. Essentially, we have a special router that is designed to deal with virtual LANs, and it will have a trunking port or a router interface that is set up as a trunking port. And so all of that communication on the VLANs will be sort of funneled into a trunking line or a trunking port on your router. Multi-layer switches, this is where things get a little bit weirder or a little less intuitive. Generally, we think of switches as layer 2 devices. Many of them are exclusively layer 2 devices. However, oftentimes a lot of the modern or kind of corporate environment switches that you're going to encounter are multi-layer switches. Essentially, they are a switch that has some functionality at higher levels. So you can have like a layer 3 switch or a layer 4 switch. There's even certain switches that deal with application layer data. So we have it's one thing to kind of keep an eye out for. On the CompTIA exam, you'll generally see a switch referred to as a layer 2 device. However, sometimes you'll encounter where it will specify a multi-layer switch device, and things can get a little more complicated there. But essentially how these work in the context of what we're talking about here, inter-VLAN routing, is these multi-layer switches will take care of some of that on their own. So instead of passing the traffic directly to a router or requiring a router to manage that VLAN traffic, routing will happen at the switch. The routing will happen at the switch. It will use something called a switch virtual interface, SVI. So again, that's a little counterintuitive. So I'm going to kind of try to speed run recap that real quick. Generally, a switch is a layer 2 device. However, we have multi-layer switches, which have some higher level functionality. So in this case, we're kind of talking about a layer 3 switch, or a switch with layer 3 functionality might be the better way to phrase that. Essentially, what these will do is they will use a switch virtual interface, SVI, and that will allow them to manage routing using these virtual interfaces at the switch rather than sending that traffic out to an actual router. This is just a screenshot of an EX3400, and it's just an example of a switch with higher level capabilities. DHCP and VLANs. By default, DHCP requests cannot pass through a router. So again, DHCP requests cannot pass through a router by default. When DHCP relay is enabled and configured within a router, the router will pass DHCP requests and responses across the router's interface. Cisco implements DHCP relay through a configuration command called IP helper. Troubleshooting VLANs. So these are some common problems that you might encounter on a VLAN. You want to check the port assignments. Devices with incorrect VLAN assignments will not be seen and will not have access to resources that they need. The solution, change the VLAN assignments. This video covers the bulk of the concepts from Chapter 11, switch features. There's a few more concepts in the book around multi-layer switches that are definitely worth spending a little bit of time reading through that. Anyway, I hope you found this video helpful and informative, and I hope you have a good week. Bye.